I have the great pleasure to introduce Ming Ongkwan from Halliburton, US, Houston. Ming joined Halliburton in 2011 as Global Operation Director for consulting with a focus in the field development and production practice areas. He has served in leadership, operation, management consulting roles across the world, including India, Saudi Arabia, Nigeria, China, Malaysia, Indonesia, and the US. So it's a pleasure to have you, Ming, with us today. We are all very much looking forward to hearing your presentation.
Thank you, Hadi. So when Hadi asked me to speak, I asked my team, send me some ideas, right? Because the lesson learned between the underground gas storage and hydrogen storage, there are lots of stuff. So they give me a deck of 50 pages. I say, okay, but I have only 20 minutes to speak, right? That's 24 seconds per slide. I say, no, okay. But we are going to focus on more on the operations. Let me stand here so I can see. So just to start with, the different, there are a lot of similarity between the UGS and UHS. We heard all morning, right? So I think there are a lot of kind of repeats. But I like to highlight a few things, which is basically some considerations on the right side with the increased explosive risk, increased mobility, right, diffusibility, and reactive to metals, right? And this is nothing new, right? And you'll hear more about it, the next couple of days. And again, if I think about it, right, we have heard this a number of times. Thank you to Serge. This is presented also this morning. Again, I think on the soft cavern, right, is proven at scale, at least on the seasonal storage, right? I agree in terms of the fast, there's a lot of things to learn. But I think the no-brainer there in terms of the limited global distributions, right, you don't have salt cavern everywhere, right? And the porous storage, it's interesting, the infrastructure. I don't know whether it's a pro and con. Could be a blessing or a curse in disguise, but definitely there's some option there. I'm not going to talk too much about the lined rock cavern, right? That's not the topic today. I'm going to focus actually on the technical challenges. This is a repertoire of the 5 key ones, right? And I think, again, I was looking at the list of topics, right? I think a lot of people will cover 1, 2, 3, 4. I wanted to focus on the material selections, right? That's, the team decided, look, okay, Ming, you need to focus on material selection. I think this is an area that is very interesting. So that's going to be the focus for today, right? So in terms of well integrity, the loss containment in the case of underground gas storage, right, is the primary mode of operation failure, right, compared to the geological. So and if you translate it to hydrogens, as we seen earlier, right, because of the hydrogen properties, it must be accounted during design, and also the fast cycling, right, added to the problem. But coming back to the well integrity risk, now you're opening up the box here, right? Completion systems. We are dealing with tubing, packer, casing, right? That's an area we need to pay attention to. Cement barrier, right? Poor annular cement integrity, damaged cement barriers, legacy wells, especially those in many places in depleted, right? Reservoir, depleted gas reservoir, you have so many depleted, similar to the CO2, the challenge is the same, right? And geological damage, well damage due to seismic activity, for example, right? So I think the question again, right, zooming in into the component needs to maintain structural integrity, right? The picture on the right shows in orphan wells, this is lots of them, right? A few millions in the US, orphan wells bubbling like this, right? Releasing methane to the air, which added to the global warming. Right, so what drives the loss of well integrity? So I'm going to focus on 3. Right? So the metals, the elastomer, seals, and the cement, right? So if you look at the components on the casing and tubings, the challenges are metal embrittlement, low permeability seals, right? And the considerations are, the selections of the metals, and also can you inhibit some of the corrosions, right? So these are some of the inputs. On the completion design, again, metal in bitumen, there are a lot of metals in the completions. And also, in addition, the elastomer, right, the rubber. So a lot of the seals, right, that goes into different parts, packers, seals, O-rings. And on the zonal isolations, it's primarily insulating between the well and the surrounding rocks, right? So those are different areas. And so this is the bigger pictures. Let's go inside. I thought it was worthwhile to kind of show this. I was kind of I'm not a chemist, right? But somebody's, and not a metallurgist either. But this kind of interesting to see how the embrittlement, how to say it, mechanisms, right? So the carbon steel alloy absorbs the hydrogen molecules, the green stuff, right? Is the hydrogens. And it goes into the metal grain boundaries, right? Forming the bubbles, the greens, you can see. And what happened is that the bubble decreases the interparticle attraction forces, right? That's causing the metal to break, right? To pit or. But I think the takeaway is that, look, a normal-looking metal on the risk matrix there, right? You can go into the danger zone, right? The black area, very quickly, right? And it's not obvious sometimes, right? So this is the mechanisms of the embrittlement, right? So this is one of the key risks that cause, the cracks and then therefore, cause the leaks in the system, all right? The same thing with the rubber, right? And hydrogen diffuse into the components, the rubber internal structures. And in this case, then, when you have the cycling, the pressure cycling, right, the rapid compression, decompressions, then it causes swelling, blistering, and you see the diagram there, it pitted the rubber, right? So what should be the guideline? So I'm listing it here, right? There is a lot of depth in this in terms of the material selection, so for both. And this is the fundamental issues that is faced by the industry. There is no guidelines, right? There is no standards. The standards are still being developed in a lot of places. So the question is, what should be the minimum standard, right? What you should go against. It is, so on the left side, on the metals, type, strength, chemical compositions, the temperature, He is hydrogen and embrittlement, right? It's more active at the lower temperature. Hydrogen content, other impurities are also taken to be consideration, and also the welding and casting, right? And on the right side, the type of chemical compositions, right? And I'm not going to read everyone. You read much faster than I do. But I think the point is that, look, if you look at the many organizations, scientific organizations, as well as the SP are looking into this area, right? What should be the guideline? I think we are doing quite a number of tests, and in the next slide, I will show you a little bit about what testing do we do, right? But before that, let me kind of cement. Cement is also again very important elements, right? And the objective is to isolate primarily the injection zones, but also the intermediate zone and possibly to the surface, depending on the cap rock, right? So one of the first, when I asked the kind of the field, right, what should be the lesson learned on cement? Number one, they say without hesitations, it's make sure it's not about just the material, but make sure it is injected properly, the cement, right? Make sure it is placed properly. So on the left side, preparing for the borehole to maximize the cement bond integrity, it is one of the most important, right? The second part is centralizing, make sure that it is not sit against one side of the wall, so it causes imbalanced kind of cement placement. These two, the best practice, it's above, more, I would say not more important, but it's as important as the material of the cement selections, right? And on the right side is the cement selections. And elasticity is also an important kind of considerations to do this, right? So this is an example of type of cement, the ranges that you have. So in order of effectiveness in terms of providing, reducing the risk to the barrier, right, for barrier risk. So the first one is the resin cement, which is basically epoxy resins, right? It's highly elastic, very low permeability, which is ideal for this kind of environment, and also highly chemical resistant. The chemical, you don't have issues in the hydrogens directly to the cement, not so much, but it is all the other stuff in the well. H2S, right? Maybe CO2 when you have high CO2 cuts, especially in the depleted field. So those are the kind of the gold standard, right? If you want to do that. And then you have others, non-Portland cement system like Thermalock. You have resin-modified cement systems and modified Portland cement system like the Corosand. So these are kind of example of different cement type and the ranges, right? So again, the question is that what is your risk tolerance? Which one should use? Right? Many different companies, many different countries. Actually, they're still debating, right? What is the right one, right? And for what sections? This is the discussions that's at play at the moment, right? Not unsimilar with CO2 actually, right? You know, which one you should use. And what is the tolerance, right, in terms of leakage rate? Right. So these are the different options. What does people do in terms of the testing? So we are going to this is the basically on the pictures on the top. This is the sub that is used for the Gasuni well, right? This is the testing. And you can see on the right, the bottom right side, the pieces of metal there, right? That is different color there. Let me see, right? These are the pieces of metal, and that is being tested, right, in there. So it was, I believe it was exposed 9 months, slightly more than 9 months, right, in the well. Temperature about 44 degree, and 100 to 200 bar approximately. I think that's the conditions. And what was tested was 14 alloys, elastomer, the 6 barrier coatings in terms of barrier preventions, and also wells, right? So this is kind of what is tested. Originally, we wanted to kind of push to kind of share the result, but the result is not ready yet. In fact, I have here Gertjan, who is the specialist, right, on the completion, and he will be going to Singapore. Our Center of Excellence for Material Science is in Singapore, and we will be continuing to kind of test what, also for the sub-safety valve, right? That's what it is. So just kind of as a summary, right? The technology is continue to progress. I think operationally there are not that many, right? We have a handful. We heard this morning in terms of, you know, the actual either salt cavern and probably 2, 3 of the depleted, right, gas. This is still experimental, but I want to hit that. Look, I think the standard methodology and the international standard is still very much lacking, right? This is phase the adoptions of the hydrogens, especially around the well integrity, right? I'm not going to cover 3 and 4, the commercial society. I think throughout this week we will have a lot. But I would invite you for questions. I think we have a lot of time for questions. And I would like to take advantage of Gertjan here, who will support me on answering, especially a lot on the metals or the material science.
Thank you very much. Thank you very much, especially for the fact that you addressed the topic that is less academically presented, and it's a kind of a dark zone for us.
Yeah.
That's good. So we have questions here. I go to Sam. You take a break a bit. You just have it after Costa.
Just two questions. So the first question is, you've taught us about the technical standards of subsurface safety installations. So my question is, what are the current activities from a global player like Halliburton is for technical standards for packers, safety valve and so on? That is the first question. And the second question is, I think there are also existing standards, for example, the ISO standards or NACE standard for saw gas service, which led a percentage of H2S. And I think it's quite similar to hydrogen usage. So what are your activities from a global player for this subsurface safety installations?
Gert-Jan, do you want to answer? Come in front. He's the specialist on this area, so I'll let the experts speak.
I'm not the expert in standards in general, but as Halliburton, we participate in all kind of committees that are involved in setting up the standards globally for packers, subsurface safety valves, everything. So as such, we are involved in the discussions if these standards come up. For carbon storage, hydrogen, maybe some for geothermal. We all realize and recognize that the current standards for oil and gas equipment do not fit one-on-one onto either hydrogen or CO2. CO2, we have lots of issues, especially on safety valves with temperatures. Normal safety valves are only tested and qualified to -7. For CO2, we go to the -80 in some instances, etc. So we need to do something with those standards. The same when we had the project with Gasunie, and Beth knows it as well. Hydrogen, there's no ISO standard for hydrogen on either subsurface safety valves or on packers. So for the approach that we took on this one is, first we did not have any H2S requirement for the equipment for the Gasunie project. And secondly, for the subsurface safety valve, we wanted to apply a test program to the valve itself, realizing that there's no international standard. So we took the standard API 14A specification, adopted it somewhat, and during the testing and the whole installation with the Gasunie, we did several flow tests on a subsurface safety valve to see certain trend statistics on the valve on how it would behave in a 100% hydrogen environment. So does that answer your question? So basically, we are involved in standards when they are being discussed, and we know that setting up a standard takes years. Also API and ISO, from what I understood, separate more or less again as well on standardization, whereby at a certain point they were more or less the same. So we will be involved and we will add our knowledge to when those standards will be written.
Just one additional question. So, but you're doing this test with hydrogen in situ with the Gasunie project, but also my question is, do you have like something like basic research and development, for example, to check all the materials you will use in the safety valves in the packers, for example, the high yield strings materials? So I think a lot of material questions could be answered via basic research and development to check these types of typical materials which are used for these devices.
Okay, on the Gasunie project, I mean, which was for us the first in the world, the approach that we took at, okay, Halliburton being an American company is, I wouldn't say conservative, but with all the things, we take care of ourselves and we protect. So typically when Gasunie came with the question, Halliburton, are you interested? The first answer was basically from, what's the scope? It's going to take you 3 years, internal development, and it's going to cost you $2.5 million. And then Gasunie said, okay, we don't have the time to do it. We didn't talk about the money further, but it doesn't take, we didn't have the time. So Halliburton management was involved on a higher level. We had a meeting with GasUnie on a different subject. The question was asked, do you have 5 minutes? So we want to explain to you what our intention is, and are you still interested? The 5-minute discussion became a 3-hour meeting, basically, and at the end of the day, management said this is something that we need to step into. For Halliburton, I think at that point it was a real mindset and a change of working, since GasUnie gave the guarantee that it is a test. So we keep all the safety precautions on a high level. If something happens out with what we plan to do, we stop, we shut it down. So in that respect, there were assurances enough for Halliburton to say, okay, we go in it, we step in it, and we work with GasUnie on this particular project. Then the next question was, okay, what are the well conditions? And what do we know? I mean, hydrogen on a big scale like in this wasn't done that much. So we had our material people and scientists look into, on their experience, what is there in the available in the world as far as writing and all that stuff. And based upon that particular experience from our people, together with information that we got from GasUnie as well on advice from their metallurgists, we said, okay, this particular material that we finally selected for the equipment is the best in this particular condition. And that was discussed, and from there on we built the designs and we built the actual equipment, installed it, and then got it done. In addition to that, we had the opportunity from GasUnie to install the test sub, like what Ming was showing. And basically the test sub, what you see here, is on the top right picture, you see 3 assemblies. The 2 at the bottom with the orange caps on it are basically fixtures that contained 64 metallic samples, varying from a standard alloy L80 material going into the ink alloys, the inconels, the Hestalloys. We even had samples in there where we welded pieces together. They were put in there around the whole OD. They were put in certain strains, all in different strains, so we knew what kind of stress levels we had. And they were exposed to 100% environment during the entire test period. So when, that's the 2 bottom ones. The top one, actually you see the exploded view here in the bottom. And what?
You want the point?
Which one?
Yeah, the top one.
This one?
This one, yes.
Oh. Oh. How do I
more.
get back? One. Okay, so this one, actually, this is not a metallic components. These are elastomeric items, varying from the nitriles, HNBRs, to the avlases, to the calreses, whatever. They were not stressed. They were just put in there, kept in place by this metal wire here, you can see here, and they were exposed to it as well. So when we retrieved the completion back in, I think it was end of January, February, whatever, all that was dismantled. All the pieces were sent to Singapore. We also sent the packer and the subsurface safety valve back to Singapore. And next week I will be there. We'll take it all apart and we're going to do a kind of an inspection to the components itself, on top of all the test samples that are being evaluated as we speak. So from that, we have, I hope we get the knowledge and the experience to sustain what we thought initially, where we started off with, like, this is the best material for this particular environment. So we've got a packer to show it, we've got a safety valve to show it, and we have all these metallic samples from that particular test set to show that what we did was the way to go. And if not, like I discussed with Hein earlier, you learn from your mistakes, maybe we need to take another route, but at least we know it. So it's a real valuable tool.
Sam. Yeah.
Thanks. So I think this is the first talk that has discussed the embrittlement issue, and I was just wondering, in a qualitative sense, the degree of the issue, if it's known, if you're repurposing natural gas storage sites, for example, does it imply that you need to drill new wells or refurbish old wells? What is the degree of the issue with the steel embrittlement?
We get a lot of questions of, can we use existing wells, especially in depleted reservoirs, can we use existing wells, existing completion equipment, and change the environment into a hydrogen environment? First questions I ask always, okay, what's the content of the hydrogen? Because it does differ. Typically what we see, and I think for Iraq we had it sometimes as well, there's only so much of a percentage of hydrogen rather than 100% hydrogen. So that does have an effect. But the approach we take typically is, do you know what you have in your well? Since these wells typically 20, 30 years old, people have no clue anymore what's in there. There's no paperwork to sustain what it is. And basically, we say, based upon the knowledge we have today, low alloy steels, more or less, like it was mentioned already before, is probably the best in this particular environment. That doesn't mean that if you have the Incolloys, the Inconels, whatever in there, it will not work. But the lower the grade of the material, the better it almost is. So we say, okay, if we have traceability, we know what's in there, then we say, based upon our experience, yay or nay. If you don't know what it is, you don't have traceability, we say just pull it out and install a new one.
Thank you for your talk and your comments and responses. Ipsita Gupta again from Louisiana State University. My question was very similar to what Sam asked, but from the perspective of where I come from, which is Louisiana, Gulf Coast, Gulf of Mexico. We have a lot of legacy wells. And so, US is venturing towards hydrogen storage, subsurface hydrogen storage beyond the 4 salt caverns.
Mm-hmm.
Now, one thing I always wonder is, we will come up with new material with time, and we will improve on them, but with tens of thousands of wells, every, I don't know what, 1,000 feet, 500 feet or so. What do we do with those 100-year-old wells that are there, even if we go and plug them, which is a massive effort that our government is taking right now of the 4,500 or so abandoned wells unplugged in our state. But at some point, the hydrogen is going to encounter those very old material that's in the subsurface, even if it is newly plugged. And we can't simply just take out thousands of wells and repurpose them. Has your company or has the industry thought about this? Because there is a lot of incentive and push into subsurface hydrogen storage in both Texas, Louisiana, Gulf of Mexico area, or anywhere else in the world where there's a lot of legacy wells. What are you going to do? How are you going to advise your operators?
Yeah, so
Thank you.
maybe a parallel around CO2, right? So the first thing you do is to understand when you inject it, where it goes, right? The plume predictions, right? The forecasting. That's the first thing. And that direction, imagine if you have 50 wells to the north and 50 wells to the south. And if the plume goes to the north, you don't have to worry about the wells in the south, for example, right? That's kind of why the idea. But almost a lot of people, almost the standard practice is to do risk assessment of leakage parts, right? So that's, you do risk assessment and see what was the issue and how bad is the risk, right?
Yes, but right now we don't have any way of fixing any subsurface corrosion that might happen over the long term.
No. And that's why I think the material exposure, right, it gives you an idea, at least a hypothesis on, what was the effect.
See, in general, as service companies, we supply materials meeting the specifications that are specified by the operators, which is a momentum basically. We don't control the well conditions in 5, 10, 15 years. And they may change over time. So it's difficult for us to say, okay, you need to do this or you need to do that. I know pulling completions, pulling it out, might be sometimes an operation which is impracticable, it's costly, it changes the economics. But yeah, that's something that as a service company, we can only help, but we're not in control of that well. So that's the whole thing.
We have also online people. There are plenty online also colleagues attending. So there are questions also posted online. One is about the rapid cycling that we may expect with hydrogen and different nature of operating well compared to, let's say, natural gas or CCS, etc. Beyond embrittlement, would there be also consideration for mechanical testing or safety assessment or the impact on the elastomers when we have rapid cycling, for example, compared to lower frequency cycling?
Do you have specific?
Now, rapid cycling, especially in hydrogen wells, has a lot of, not as much on the metal as such, but more on the elastomers itself. One of the slides that Ming showed was about the effect of explosive decompression, and where it's like, yeah, this one. Yeah. So explosive decompression for hydrogen is really a serious issue to be looked into. In principle, the seals that we provide, the majority of the seals are all suitable for hydrogen, but they can always be affected by this explosive decompression. The only way you can counter this is by procedural release of pressures. So we within Halliburton have, and all the operators have certain steps and procedures whereby you release a certain pressure over a certain time in order to minimize or at least to allow the hydrogen to come out of the matrix of the rubbers again, so you avoid that particular problem. If you suddenly release it and the hydrogen can't release out of the rubber itself, you get that effect. And once you have that effect, your seal is gone, and then your integrity is gone, and your barrier is gone. So that's a procedural issue.
Yeah, I was also triggered by the question of these legacy wells. I was thinking, would that also be an additional argument maybe to go for virgin aquifers to deploy underground hydrogen storage versus maybe already deployed areas?
We could, and that is in the books, but the wellbore structures and the casings and the cements will be in the aquifers as well. The aquifers will be shallower. The oil and gas reservoirs are generally deeper. And in Gulf of Mexico, they are stacked actually, so sometimes they're even sandwiched between multiple oil and gas formations. But the wellbore will go through them. And especially with hydrogen, CO2 may not migrate as much, but hydrogen, once we go beyond salt caverns, it's just so mobile. It's going to, it will intersect legacy wells. And that also brings us back into the social acceptance thing, because then, why should someone, and we get this a lot in Louisiana, even with CCUS, there's a lot of pushback from common folks that, not in my backyard. Thanks.
More questions? Yes, Rahul, we go there, and then we have the break.
Yeah, of course. I enjoyed this talk very much, but I was thinking about something. Are we over-engineering things? Or what's the limit of testing? Because I saw the presentation by RAC earlier, and they said, okay, we use L80, and we use all, they use a lot of the standard stuff available, and seemed to work fine. Of course, we need to see with time. When do we know, okay, this is enough for something like hydrogen? There was a comment made about, us being sort of cowboys in this game. How much of a cowboy should we be when we look at hydrogen?
American question.
Yes.
Testing is an interesting one. In lots of presentations and discussions I have with operators around the hydrogen well, the well designs, is that all the operators want to test. And then I ask them, what do you want to test? And then they tell me, you tell me what I need to test. So it's a kind of a vicious circle. And basically we say, we don't know what they want to test. I mean, first we need to know the environments and why do they want to test? Is it just to give them a good feeling? Hydrogen, it is an area that has more attention, has more attraction to people. But like we mentioned in other discussions had it as well, we use basically common oil field components. The standard safety valves, the standard packers, the standard nipples. We use standard materials. Only the environment is different. And because there are no ISO standards or API standards, people feel somewhat uncomfortable. They go into a territory that they are not used to. They got a manager saying, and you shall make sure that it works. And the only way to justify that it works is, we test it, we test it, we test it. And yeah, I got doubts about whether the tests really add any value to it. In hydrogen, we know for CO2, where we go into really the extreme temperatures, everything, it really adds value because it may have an effect on the mechanics. But in general, in hydrogen, basically we say the equipment is there. It needs some tweaks as far as metal selection, based upon the knowledge we have, based upon the knowledge we gain from what we've just tested. But apart from that, it's business as usual, as far as I can see it.
Very good. That was an excellent session, both of you. Thank you very much. Let's thank them both.